there's where he is now. He works broadly in branching processes, stochastic geometry, and mathematical finance. And today's talk, he's going to talk about his recent work with his PhD student on a mathematical finance problem.
Thank you. I would like to thank Sandeep for the invitation, and I was wondering what I should speak about. And so whenever I usually occasionally dabble in math finance whenever I get some co-conspirators, and one of them is here in the audience, Purba. Um, so all questions can be directed to her. Since this is a diverse audience, I quickly put together a couple of slides of introduction. And I hope, my apologies to those who are not familiar with this area uh, for the very brief introduction. And I hope it sets up the context adequately. And for the experts, I hope there are not too many inaccuracies or lack of nuance. There are some, even though the title is European options, the first part is on European options, and the second part is more interesting for exotic options. And we have one example as well included there. So to get started, so we consider a market which consists of a tradable risky asset and a money market. We will assume that the interest risk-free rate is 0 for the purpose of this talk. And what derivatives are, they are contingent claims. So these are claims on the underlying risky asset. And for much of this talk, you can think of these claims as being, let's say, a simple plain vanilla European call option, which promises the buyer of the contract a payoff, which is ST minus capital K at time capital T, which is the maturity time. And this capital K is the strike. So it pays ST minus K if ST is larger than K, and there is no payoff. The payoff is 0 if ST is below K. So what is in this for the seller? The seller charges an upfront premium for selling this contract. And these contracts are typically very useful for risk management and also for taking speculative positions in which your downside is limited for a small upfront fee. So there are two questions here. One is, what should be the fair price of this contract? And the second question is, for the seller, the downside is unlimited, right? The stock price can actually be very high. And so the person selling the contract may be hit with a very large liability at time capital T. So the contract specifies this time, maturity time capital T, and the strike price K. These are written into the contract. And there are various other, so closely related with the pricing is also the question of hedging. So the seller of the contract, who is said to have a short position in the contract, will set up a hedge that is comprising of certain positions in the underlying and certain cash positions. It could involve borrowing money, and in such a way that at time capital T, you cover the liability, right? So your portfolio is such that the value of the portfolio equals whatever you may have to pay out. And there are various other options, such as American options, exotic options, and credit derivatives. The other option that we would briefly mention in this talk is, say, a simple Asian option, where instead of ST, you look at the average value of the stock price at two different times, small t and capital T, and look at this would be the payoff. So whatever is the payoff, it's kind of written into the contract. And there are two questions. One is, how do you price it? And how do you hedge the risk, right? So we assume that the market is frictionless. That is, there are no transaction costs. Typically, you will have a bid-ask spread. So if you buy a stock and immediately try to sell it, you would be incurring typically a loss, right? So the fundamental idea here in pricing is to assume that there is no arbitrage in the market, which implies that there exists a martingale measure. That is, there is a probability measure under which the underlying process is a martingale. Now, a market is said to be complete if there is a unique martingale measure. When there is a unique martingale measure, there is a unique price for the claim. which is nothing but the expectation of the payoff given the information up to time small t. So this is the price at time small t of this claim. And one can show that in the simplest situation, you can perfectly hedge all the contingent claims. A market is said to be incomplete, which is what is the situation typically in markets. There are many martingale measures, and so there is no unique price. And in this case, not all claims are attainable. So you cannot perfectly hedge the claims. So in pricing, there are two approaches one can take. One is model-specific pricing, and another approach is model-free or robust pricing. So in model-specific pricing, what one does is one assumes a particular model, such as the geometric Brownian motion, or the Merton's jump diffusion, or you can have stochastic volatility models, such as the Heston's model, time series models like the Garch. There are local volatility models. There are models for the market microstructure, such as the Hawkes processes, which model the arrivals of of the buy and sell orders and their scaling limits. There are also Markov switched models where you assume that the market is can operate in various regimes, and these regimes can switch, which would change the underlying drift, volatility, etc. There is the structural approach to modeling where you try to model various stylized characteristics in the data. So you look at the historical data and try to capture many of the characteristics that you observe in the data. And in the reduced form, and you estimate the parameters based upon historical data. Whereas in the reduced form modeling, what you do is you look at liquidly traded options and you try to fit your model to the price that you observe for these options, and then use that model to price more exotic derivatives. Now, of course, the advantage of model-specific pricing is the ease of calibration, and you have a few parameters. You can actually very easily calibrate, simulate these processes. Computation is also easier, right? So many times the price is given by certain PDEs, which you can solve and come up with prices. Okay? But of course, this involves modeled risk, right? Now, in model-free pricing, what one does is one assumes that you are given the prices of liquid options at certain times, and you try to infer the price, the distribution of the marginal distribution of the stock price at these times, based on the prices of the liquid vanilla options. And then what one does is derive price bounds by maximizing or minimizing the payoff over all martingale measures which have these specified marginals. So this is model independent, and you are simply using the price of these liquid options that you see in the market. And this leads to what is called the martingale optimal transport problem. And there's been several recent work in this area. The dual of this problem leads to what is the super or the sub hedge for the derivative. Now, of course, this is computationally quite intensive, and since this is an optimization audience, there are many challenges that we are facing with regard to carrying out some of these numerical experiments, and we would be very happy to discuss with experts here on how to go about doing some of these numerical calculations. Now, when it comes to hedging, there are, again, two approach one can take. One is the dynamic hedging, where you keep adjusting your portfolio frequently. And the other is static or semi-static hedging, where you, in static hedging, you set up the portfolio at the beginning and then you don't touch it. It remains what it is through the period of the, until the maturity period or until the hedge expires. In semi-static hedging, you infrequently you may adjust your portfolio position. So the dynamic hedging is typically a delta hedge. Delta hedge is you take a certain position in the underlying stock, which is the derivative of the call price at the value of the underlying. And so the theory tells us that you should continuously modify this position in order for you to be perfectly hedged. This involves a lot of transaction costs if you keep on adjusting your portfolio. So typically what happens is that you adjust it either daily or if the position changes beyond a certain threshold. And then of course you sometimes also adjust these hedges for model risk. In static or semi-static hedging, what one does is your hedge portfolio consists of a combination of liquid options, certain stock positions, and money market cash positions. The hedge portfolio is typically set up at the time of initiation of the contract, and it is adjusted infrequently. So why static hedging is attractive? One of the reasons is that there could be large abrupt movements in the asset prices, triggering circuit breakers, trading halts, and a widening of spreads, leading to increased risk aversion among investors and a consequent drying up of liquidity. In such cases, application of dynamic hedging strategies becomes difficult, expensive, and often faulty. So this is what makes static hedging kind of attractive. So you set up your static hedge and you forget it. Right? So I would just describe a strategy that was proposed by Carr and Wu in this paper in 2014, and then see how we have tried to extend this result. So what they assume, so the assumption is that the asset price is a Markov process. And what one does is to hedge a long maturity. So this capital T is the maturity of the option that we are trying to hedge. That's called as the target option. And what one tries to do is to hedge this long maturity option with a continuum of options, liquid options, all sharing a common maturity, small u. Okay. And the way one does this is to express the target option as a weighted combination of options that mature at time u. Okay. So this small t here is some time between 0 and u. Capital S is the price of the stock at time u. So the price of the option, the target option, is written in terms of the options that are maturing at time u, where these weights are nothing but the second derivative of the target option at this future time u. Okay. And in order to estimate or compute this, you need a model. Okay. So that's where this model specific. So one assumption here is that we have a Markovian dynamics. The second is in order to compute these weights, we need some assumptions, right? Because this is the second derivative of the price at a future time u, right? At the time at which these options that we are trying to use to hedge expire. So now the interesting thing to notice here is that these weights are independent of small t, right? And that's what makes this static. So you set up this hedge at time 0, and then this hedge lasts up to time u. And if you have in your portfolio this continuum of options of all strikes kappa, then the left-hand side exactly matches with the right-hand side. And no, we have option. So this is your target option, which you have sold. This is what we're trying to hedge, but using options which have maturity small u, which is smaller than capital T. No, slightly earlier. So u is smaller than capital T. Later than small t, right? So this hedge works from time 0 up to time u, at which stage these options will mature. You will have a certain payoff, and then you can set up another hedge. But if u is close enough to capital T, then you should. Yeah, I'll give a short proof. So what is the question? Is exact, right? This equation is exact under the Markovian assumption, right? And so the first thing to notice is that these weights are independent of the underlying price of the option, the price of the underlying and of small t. So that's why this is a static hedge. Yeah. Can you repeat the question in terms of? The derivative, right? So these are the particular weights that will give this equality. So if you want this left-hand side, the price of your target option to match with these options maturing at time u, you need to have the weights which are exactly the second derivative of the call, of the target call at time u. Okay. C is the price of the option. This is the, in some sense, this is the perfect hedge. So if you construct a portfolio, suppose you have available all options that mature at time u, right, of all strikes kappa, ranging from 0 to infinity, then you can set up a perfect hedge. So your portfolio consists of WK units of options that have maturity u and strike kappa, right? So that's the assumption. This is true for, no, in this case, so there is some, so right now we are just looking at European option. I think Carr and Wu probably have something on exotic options. So I don't know exactly what they're. Right. Here it is just the plain vanilla, right? And these weights are nothing but the future gamma of the call. And so in order to compute this, we will need some model. So I'll give a very quick sketch of the proof. The proof is just 2 lines, and I thought maybe this may clarify things leading to what we are doing. So by the Markov property, so one can, it turns out that the price of the option at time small t is nothing but the conditional expectation of the price of the option at time u. Okay. So this is just the Markov property, and this is the transition density of the underlying. So this just follows, so this is where the Markov property is used in order for you to be able to write this equation. Once we write this, then there is a result of Breeden and Litzenberger, which tells us that the transition density of your stock price process is the second derivative of the stock price with respect to the strike K. Okay. So these are options that are maturing at U, and this is your target option price at time small u, right? And as you can see that all you need to do in order to get your the relation that you want is to integrate by parts, because the derivative is just getting swapped here, right? So we want to include these options in our hedge, and the weights are given by the second derivative of the target option at time u. And so you integrate by part twice and use some natural boundary conditions, and what you end up with is this equation on the left, right? So the target option is exactly equal to this integral here. Now in practice, of course, you have liquid options of short maturity available only at finitely many times. And so you will need to approximate this integral here by the sum, and the weights Wj and kappa j here are chosen based on some discretization rule, for example, the Gauss-Hermite quadrature process. Okay. Now, as far as the performance of this is concerned, the performance is comparable to a delta hedge for the Black-Scholes model, and it outperforms the delta hedge for the jump diffusion model, even with a very small number of options in your portfolio. But the model risk kicks in when you go beyond this Markovian framework. So for example, if you try to apply this to a Heston's model, then the performance of this will deteriorate. Okay? That's where the model risk kicks in. So what we try to do in this first part of the talk is try to extend this result. Now, one thing that one observes is that since we are doing this discretization of this integral, these points Wj and kappa, these strikes are chosen according to this Gauss-Hermite quadrature rule. Now, typically what happens is that these strikes are spread quite far apart. And if T is large, there would be very few liquid options with maturity U close to capital T. So we would like to fix these two problems. And what we would like to do is to include liquid options with short maturities of various short maturities. Here it was, you can include only liquid options in your portfolio of one particular short maturity. There are two things we would like to achieve. One is to include liquid options of various short maturities that are available in the market. And the second thing would be to, as time evolves, as more liquid options become available, we would like to incorporate those as well into our portfolio. And the way we do that is so this is our Carr and Wu relation. We suppose that we now have liquid maturities of at times U1 and U2 that are available now at 2 times. So I'm replacing this U by U1, and we have one more short maturity option available at time U2, which is less than U1. Let's say, and we will see how we can incorporate these liquid options as well into our portfolio. So, and what we do in order to do that is we assume that the liquid options at this longer maturity U1 is available over an interval, let's call it K11 to K12. So these are kind of bunched, typically near the money. It need not be just one single interval, but for just illustration, we are just taking it to be one single interval. So let's say these options, these liquid options at time U1 are available in some interval K11 to K12. And so what we do is with this integral from 0 to infinity, we split it as the integral from K11 to K12. And I'm replacing this kappa here by kappa 1 and U by U1. That's all I'm doing. And plus the remaining part, right? So the remaining part is 0 to K11 and K12 to infinity, right? And now what you can see here is that these options that are maturing at time U1, I can apply the Carr and Wu relation again and try to write a relation for this in terms of options that mature at time U2. That's all. Nothing complicated here. So use the Carr and Wu relation to write the CST kappa 1 U1 in terms of options maturing at time U2. Use the Fubini's theorem and rearrange. And what we get is an equation like this, where we have now been able to write the target option in terms of options maturing at time U1 and U2, where this W kappa 1 is the original Carr and Wu relation, the second derivative. And this W tilde 2 is now a combination of the original weights plus something else, right? That's not hard to see. And one can now iterate this process to as many short maturities as one wishes. And you can explicitly write down what these weights are, right? And so a lot of extensive numerical analysis has been done by Purba for this kind of setup. You can look at this paper for various different situations. So I'll leave with just two simple pictures, which will kind of illustrate how this kind of works. The first one is for the geometric Brownian motion. And what you have here are these various implementations of this Carr and Wu model. So we have the 5th and the 95th percentile of the shortfall between the target option and our hedge. And effectively, the hedge expires at this point, roughly around 0.8. The target option continues beyond that. I don't quite remember exactly what the expiry of the target option is. And you can see that this is the time at which this time U2 at which the short-term options expire. And you can see that including a few short-term options of time U2 actually gives you much tighter bounds on the shortfall as compared to just using the same number of options expiring at time U1. And at this time, there are several options that one can consider. One can, from the payoff, one can reset the weights. I mean, you can use that iterative relation to recompute the weights. And okay. So you can do a semi-static hedging. And this is the picture for the Mertens jump diffusion, where to just point out what the modeled risk is, we have also included what the performance of the delta hedge looks like. And as you can see that the performance actually, the negative side is the actual shortfall. I mean, this is the hedge minus the price of the target option. And you can see that it kind of deteriorates quite fast when you have when you have jumps in your model. Okay, whereas this our process actually gives you much tighter bounds on the shortfall. So now we move to the second part of the talk, which is model-free hedging. I'll just briefly describe what this model-free approach to pricing and hedging is. Are there any questions on this part? So now we consider a very simple market where we have two trading times, U and capital T. And we have a derivative with payoff that depends upon the stock price at time U and at time capital T. Okay. Suppose we have liquid call prices of all strikes that are available at both these times. So this is the assumption. So we are assuming that we can observe liquid call prices at time U and time T. And Breeden-Litzenberger then tells us that this specifies your marginals at these two times. Okay. So the model-free upper bound for the price is you look at some probability measure which has the marginals, the specified marginals mu and nu for x and y, and these are all measures, are all the martingale measures with these given marginals. Okay, and you try to maximize this price under all martingale measures with specified marginals. So the first two conditions, these are the marginal constraints, and this is the martingale constraint. Clear? And so no arbitrage implies convexity for the stock prices and convexity for the option prices. So for any given strike K, as the call price at times U will be at most the call price at time capital T. As uncertainty increases with time, your call prices would increase, right? And this is a result of Mueller and Stoyan tells us that this implies that these marginal measures mu and nu satisfy this convex ordering property. And the result of Strassen tells us that this is equivalent to the fact that there are martingale measures with these specified marginals. So this set here is non-empty. And one can write down the dual to this problem, where the dual consists of kind of a hedge in plain vanilla options and a position in the stock. And this is the constraint. So the objective function comes into the primal comes into the constraint here. And this gives us a kind of super hedge for the price bound for our option. Okay. So there are many results which are similar to what you see in optimal transport literature. Under some mild conditions on your payoff function, you can prove a strong duality. That is the optimal values for the primal and the dual match. And also under some additional conditions, one can show that the dual minimizer is attained. So you can set up in principle a hedge which will match with the price of the upper bound on the price. And similar results are there for the lower bound as well. And of course, if you have further conditions, you can actually specify that you can show that these optimizers have a certain nice properties. And if the marginals are discrete, one can actually also construct these things precisely. The characterization, that is exactly what this does, right? So when you have this condition on the payoff function, then you can show that this measure, the optimal measure, is what is called as a left monotone transport plan. And you can actually specify exactly what this would be. Of course, if you want to do it, if mu and nu are continuous measures, then this has to be done numerically. Whereas if the mu and nu are discrete measures, then you can actually, there is a nice formula by which you can actually say what this plan would be. Now, in the discrete case, now what happens in practice is that liquid call options are available only at finitely many strikes. Now, if there are only finitely many options, now if you recall the previous problem that we set up assumes that you have liquid call options of all strikes that are available that would uniquely determine the marginal distributions, right? The mu and the nu. But if you have only finitely many call options that are specified, then there are infinitely many marginal distributions that will be consistent with the observed call prices, right? So your problem translates now into optimizing infinitely many martingale optimal transport problems because even the marginal measures are now not specified uniquely. However, a result of Nicole, I don't know how one would pronounce this, and Daniel Schmital's shows that if C has certain nice properties, like it's directionally convex, then this supremum, this optimization problem on the left-hand side is equal to the value by looking at a martingale optimal transport problem where the marginals are this mu star and nu star. So what are mu star and nu star? These are the marginals that you obtain. So you have these call option prices observed at finitely many points at time u and capital T. You linearly interpolate between them, okay? And when you do that linear interpolation, you can then come up with these mu star and nu star. There are discrete marginals which are consistent with this. So now once you linearly interpolate this, you have now call option prices available at all strikes, right? And then that uniquely determines your marginal distributions mu star and nu star. And because of convexity, one can then observe that these mu star and nu star will dominate any measure that is consistent with the observed call prices, right? And the nice thing about these measures is that you can write a very simple formula for what these measures are. These are discrete measures. This k sub j's are the strikes at which you are observing the call prices. And the measure mu, which is consistent with these observed call prices, is just this discrete measure, which is supported at these strikes. Okay, so there's a very nice, so the point of this slide is to say that, look, the very, very simple formula by which you can specify what these marginal measures are when you linearly interpolate these call prices. So you have fixed your measures mu star and nu star with some nice properties. And similarly, you can find nu star as well. Okay. So in the discrete case, if the marginal measures are discrete, then the martingale optimal transport reduces to the LP problem, where Pij's are the probability that at time u, your stock price is xi, and at time capital T, it's yj, right? And these are the marginal constraints, right? So sum of Pij over j, it's alpha I, sum over all I is beta j, and this is the martingale constraint, right? Now, of course, once you have these discrete approximations, the natural question would be that if you have more and more call prices that are observed, and this mu k and nu k converges to the original measure mu comma nu, will the solution also converge, right? So one can ask such questions, and what is the speed of convergence? And there are some papers in the literature which tells us when this convergence would happen. There are some moment assumptions under which this Gu and Obloch prove such a convergence result. They show that you need to relax this martingale constraint. It's called an epsilon relaxation of the martingale constraint, where the epsilon goes to 0, but it can't go to 0 too fast. In that, under that condition, they show that this convergence would happen. There are similar results in this other paper that I had mentioned earlier, but for compactly supported measures. So now we come to the problem, our problem formulation in this situation. So this is the pricing problem, right? And then you have the super hedge here. So we can find the price bound for an exotic option. And if the price is outside this bound, then there would be an arbitrage, right? But this super hedge that one has can be quite expensive, okay? And these price bounds can be too wide for any practical applicability. That is one of the problems with this model-free approach that one encounters. And one thing one can do is to try to incorporate additional information. So right now, the only information that is being incorporated is that you have call prices observed at certain times, right? At the times at which the payoff of your exotic option depends. So additional information such as you can include information on the variance of the returns, but this would compromise on the model freeness of the process. One can include, one can include information on certain prices of liquid exotic options. One can include information on the marginals at earlier maturities. When there are two assets, you can impose some causality constraint, and that leads to a more complicated martingale optimal transport problem, and then you can do certain relaxation called the McCormick relaxation, and you end up with something that you can actually solve. This also has been shown to reduce this price gap between the upper and the lower price bounds to some extent. So what we do is the following. We take a slightly different approach. We say that, look, given a price, so let's say we have sold a certain exotic option at some price C naught. So the C naught would be some value in between the upper and the lower bound. Construct a hedge comprising of plain vanilla options so as to minimize the, let's say, the worst case expected potential future exposure, so the shortfall. Okay. So mathematically speaking, the way we formulate the problem is we fix certain weights W, and this H of XYW is a linear combination of plain vanilla calls expiring at time U and capital T, right? And it's a weighted linear combination of those plain vanilla calls. And the C minus H plus is the shortfall. So you look at the expected shortfall under some probability measure, martingale measure P, and you look at the worst case scenario, right? Look at all martingale measures which have marginals mu star and nu star, and you look at the worst case scenario. Okay. Of course, one could argue that one can interchange this inf and the supremum. And these weights are chosen so that the cost of setting up your hedge is at most the price of the target option. Okay. If one is interested in, so this is a martingale optimal transport problem inside, and then you are minimizing over all these weights. Okay. So if you are interested in the hedge up to time small t or small u, I mean, this should be u. I kind of change the t everywhere to u, so I don't have to keep saying small t and capital T. I forgot to change it here. Okay. So this is at the shorter time u. If you are interested in the error at time u, then one would probably have to look at a modified martingale optimal transport problem, which looks something like this, where the expectation, the conditional expectation is now inside this brackets. Okay. So when the measures are discrete, so this would lead to an LP problem. And here, I think we run into some numerical issues when we try to do this one, as the number of options that we observe increases, and as the number of options we included in the hedge portfolio increases. So there are a lot of challenging computational issues that we have found, even in the existing literature, where people actually try to use this to price, say, simple Asian options with just 2 time points. One observes that as the number of observed call options increase, even in a very simple Black-Scholes kind of framework, the geometric Brownian motion framework, one would expect that the price, upper and lower price bound should collapse and converge to the actual price under the Black-Scholes model. But it turns out that at some point, I think in this LP solution, numerical issues creep in, or what, I don't know, they converge very, very slow and seems to stabilize with about 8 to 10% error. So the computational complexity, as you can see, increases as the number of call options at these 2 times increases, because the total number of variables is the product of the number of call options that are observed. And as the number of options in our hedge portfolio increases, the minimization problem outside becomes more complicated, okay? Because there are a lot of local minimas and so on. And right now we are just doing some sort of a grid search in order to compute the optimal values. But having found an optimum value for our problem, let's call it W star, we can actually try to look at the dual of this problem, right? The dual of the MOT with these weights, W star. And that would yield us a super hedge for the shortfall. And this super hedge would potentially be much cheaper than setting up a super hedge for the target option. And so the next two slides are just putting some preliminary numerics. So we have done some, so just don't try to read those numbers. We still don't have extensive simulations to put some nice pictures. So I'll just leave it with some tables. So what we have done is we have done some numericals for the geometric Brownian motion and the jump diffusion models for a plain vanilla call and an Asian option. And that's what I'm going to present. And maybe I'll point out to some numbers here, which may be what one can take away from these. The actual numbers are not very interesting. Okay. So the first number that one should see is what is the rough order of magnitude. So the spot price is 100. The target value of the option. So this is for the plain vanilla call maturing at time capital T. And we are trying to hedge it using options that mature at time U. So this is the price of the call. And when we use one single option with the strike 100, then the weights, you get some number for the weights. And this is the worst case average shortfall. And what you see in the second column is the Monte Carlo simulation, what you see actually for when we simulate these stock prices. And you can see that the gap is not very high. We have also calculated this 95th percentile. When you include two options, of course, maybe the average and the 95th percentile under the worst case scenario doesn't change much, but the Monte Carlo one does. I mean, sometimes it goes down, sometimes it can even go up. But one can see interestingly that this weight here is negative, which means that sometimes your hedge may be like taking a short position in some options of different strikes. So these strikes are kind of been optimal. So we have done also some optimization over various strikes, and these turn out to be the best. And of course, it would be nice to know how one goes about this minimization problem in W, so that we can scale this up to many more options in our portfolio, at least 4 options or so. And this is similar results for the jump diffusion. And these are results we have for the Asian options. Now here you can see that the Monte Carlo value and the worst case value, the differential is somewhat larger. And we would like to do this for many other exotic options, increasing the number of time points to more than 2. All this increases the computational complexity enormously at every stage. So I'll stop here. Thank you. Part of the optimization part. What kind of issues are you running into? Okay, maybe the right person to talk would be Purba. And see, so one thing is numerical instability, like I pointed out, right? Even as the number of options that you observe increases, the number of variables that you see in your primal goes up. Right? And so it kind of leads to certain numerical instabilities. Maybe there are better ways. Maybe one can look at the dual or something like that but for the minimization one, that seems to be the case. But here I'm not very sure. There is a min-max setup. Correct. So if you look at the problem, it's a saddle point.
where the minimization is on the weight and the maximization is on
on
a finite.
Right.
And therefore, there are.
The minimization is not actually over a compact set.
It's not.
No, it's not. The weights can,
Also,
yeah,
it could be unconstrained.
correct.
What if
The constraint is just that the total, the cost of setting up your portfolio should be bounded by the cost of the target option.
that doesn't necessarily
Bound.
Maybe one thing we do is put some kind of a margin constraint on that.
Hmm.
Typically, nobody will allow you to take.
To take very large positions.
Yeah, so if you put a margin constraint, then you'll get a compact set, which is reasonable.
Right. And then, yeah, then things would be easier.
At least numerically.
Right.
And maybe that's what it's causing.
But by the nature of our shortfall, that function, there are lots of maximas and minimas see, these are all very piecewise linear functions. And the way we are probably doing our minimization is kind of some sort of kind of grid search or whatever. If there are better ways to do it, it would be more efficient.
Then let's thank both the speakers again for the session.